Process steps for chemical milling: incoming material, degrease, clean, rinse, pickle, first stage prepare, tools and template negative, exposed areas for etching, for scribing, photo develop, rinse, mask spray, dip photo, set mask, bake, develop, second stage mask, etch spray dip, rinse, clean or brighten, rinse, third stage etch, strip mask, bench dip, rinse, pickle, hot rinse, fourth stage remove mask, post treatment if required, deliver to inspection. Process characteristics: material removal rate. MRR is chiefly dependent on the selected etchant. However, etchants that remove metal faster tend to have many side effects, which include reduction in surface finish, increased undercutting, higher heating, greater change of etch rate, attack on the bond between the maskant and the workpiece. The etch rate is generally limited to 0.02 to 0.04 mm per minute, where surface finish and accuracy are not important. The etch rates are high as 0.1 to 0.2 mm per minute have been achieved. In an aircraft industry, the material removal rate on aluminum component is reported to be about 140 cubic meters per minute. Accuracy: the undercutting behavior is simple. Contouring is essentially the same as in chemical blanking. Undercut per edge is approximately equal to the depth of cut. Each factor in chemical contouring is defined as the undercut divided by the depth of cut, which is the reverse thus defined in chemical blanking. Allowance for undercut is made in the design itself with optimum time, temperature and solution accuracy of the range of plus or minus 0.01 mm can be achieved on relatively shallow depth of cut. Figure indicating undercut in simple contouring. Surface finish: initial surface waviness and defects are not greatly altered in contouring most metals, but may be smoothed out to a certain extent. The quality of finish is lower for extrusion forgings and castings. The surface finish obtained may be around 5 micron. All aluminum alloys show better surface finish of the order of 1.6 micron meters. Hydrogen embrittlement. Hydrogen embrittlement may occur owing to absorption of hydrogen into chemical machining in some metals. Aluminum alloys are not subjected to hydrogen embrittlement. Considerable care should be taken to avoid hydrogen embrittlement in steel, stainless steel, copper alloys and nickel alloys. If hydrogen embrittlement occurs, it can be overcome by heating the workpiece around 120 degrees Celsius for 1 to 4 hours. The surface produced by the CHM process are otherwise stress-free and show no thermal effects. Applications: chemical machining has been applied successfully in many cases where the depth of material removal is critical to a few microns and the tolerances are close. The process is usually applied to removes metal from a portion of the entire surface of formed or irregularly shaped parts such as forgings, castings, extrusions or formed wrought stock. Reduce web thickness. Below practical machining, forgings, castings or forming limits, taper sheets and preformed shapes. Produce stepped webs, engraving on any workpiece. The advantages of this process are: several parts can be machined simultaneously. Extrusions, forgings, castings, formed sections and deep drawn parts can be lightened considerably by CHM. Machined or extruded parts may be reduced on selected areas or all over CHM to provide web actions that are thinner than those obtainable by conventional methods. Castings may be designed uniformly oversized but treated with little or no waspage and then chemically machined to achieve finer desired dimensions. Disadvantages of CHM: material removal rate is slow. Metal thicker than 2 mm cannot be machined. High operator skill is required. Corrosive agent damages the equipment.